Welcome to the Explainer. Forget about your everyday flat mirrors for a second. Today, we're bending the rules of reflection to understand the physics of curved mirrors, a world where light gets twisted to magnify, shrink, and literally turn our reality upside down.
So, what do these things have in common? Well, the answer lies in the powerful and, totally predictable science of spherical mirrors. Each one is a little masterclass in how a simple curve can manipulate light.
Okay, let's dive into this. Here's the roadmap for our journey. We're going to start with the two basic mirror shapes, then get into the geometry of how light behaves. We'll figure out what real versus virtual images actually means, then unlock the math behind it all. After that, we'll see these mirrors in action in the real world and wrap it up with the biggest takeaways.
Right, first up, let's establish the two families of spherical mirrors. And honestly, the best way to get it is with an object you probably see every single day.
Just think about a spoon. The side you eat soup from, the part that's caved in, that's your concave mirror. And the other side, the one that bulges out at you, that's a convex mirror. This simple analogy, it's really the intuitive key to understanding how differently they work.
So what's really interesting here is how their shapes basically predetermine what they do. A concave mirror, because it curves inward, acts like a collector. It's a converging mirror that brings light together. A convex mirror does the exact opposite. It scatters light rays, spreading them apart, making it a diverging mirror. So you've got one job: gather light or scatter it.
Let's move on and see how this builds. To really analyze these mirrors, we need a common language, a set of rules. We have to define the terms we're going to be using.
Okay, so every spherical mirror is basically just a slice of a perfect sphere. The pole, which we call P, is just the dead center of that mirror's surface. And the center of curvature, C, well, that's the center of the giant sphere the mirror was sliced from. These 2 points define the mirror's fundamental geometry.
Now this next point, the principal focus, or F, is absolutely critical. It's the mirror's sweet spot. It's the point that dictates how it messes with light. Its distance from the mirror is the focal length, F, and it's always half the radius of curvature. That relationship, F equals R over 2, is a golden rule here. So by tracing just a couple of predictable paths, we can figure out exactly where an image is going to show up. A light ray that comes in parallel to the main axis, it bounces through the focus. One that goes through the focus first, it bounces off parallel. And a ray that goes through the center of curvature, it just reflects straight back on itself. You only need to draw 2 of these, and where they cross, bam, that's your image.
Now for convex mirrors, the rules are kind of the same, but everything happens as if it's originating from behind the mirror. A parallel ray reflects away, but if you trace it back, it looks like it came from the focus. A ray aiming for the focus bounces off parallel. It's all about where the light appears to be coming from, and that is a crucial difference.
Okay, so now that we have the rules, let's explore the 2 fundamentally different types of images these mirrors can create. Are you seeing something that's really there, or is it just an illusion? This question, right here, gets to the absolute heart of the matter. Is light energy physically converging at a point in space, or is it just a trick of perception, where our brain traces the rays back to a point they never actually were?
And this table brilliantly illustrates the key differences. A real image is where light rays physically are. It's formed in front of the mirror, it's always upside down, and you can actually project it onto a screen, like a movie projector does. A virtual image, though, that's a trick. It's where the light appears to come from, behind the mirror. It's always upright, and you can't project it on a screen because, well, there's no actual light there.
Look, ray diagrams are great. They really are. But for true precision, we need to translate this geometry into the language of mathematics. We need to go from drawing pictures to making hard predictions.
And this is it. This elegant little equation relates the object's position, u, the image's position, v, and the mirror's own focal length, f. It's that simple. If you know any 2 of these, you can always find the third.
And then there's this one, the magnification equation. This tells us exactly how much bigger or smaller the image is going to be. But see that minus sign? That's the secret sauce. It also tells us whether the image is upright or flipped upside down.
Right. So the crucial point is that these formulas are pretty much useless unless you understand the rules that govern their signs. The physics isn't in the numbers, it's in the plus or minus.
This table is basically the Rosetta Stone for mirror math. If your focal length f is positive, you've got a concave mirror. Negative, it's convex. If the image distance, v, comes out positive, you've formed a real image in front of the mirror. If it's negative, it's a virtual image behind it. And magnification, m?
Positive means upright, negative means inverted. Master this, and you can predict everything without drawing a single line.
Okay, enough theory. Let's connect this physics back to the real world and see why these properties matter so much. Why would an engineer pick one type of mirror over the other? Well, concave mirrors are masters of magnification and focus. Think about a makeup mirror. You put your face inside the focal length, and boom, you get a big, upright, virtual image. Or a car headlight. You put the bulb right at the focus, and it shoots out a powerful, parallel beam of light. It's all about precision. On the other hand, convex mirrors are for when you need to see more of the world at once. You sacrifice size for a panoramic view. That's why they're on your car and in stores for security. And that warning, objects in mirror are closer than they appear? It's there because the mirror makes things look smaller, and our brains are wired to think that smaller means farther away. It's a built-in optical illusion.
So we've covered a lot of ground, from spoons to complex equations. Let's boil it all down to the most essential points, the stuff you really need to remember.
Here it is, the whole story. 1. Shape dictates function. Concave converges, convex diverges. 2. Ray diagrams let us predict what will happen. 3. The images formed are either real or virtual. 4. The mirror formula puts hard numbers on it. And 5, and this is the big one, the sign conventions are the key to translating the math back into the real world. So I'll leave you with this thought. That weird moment when you're playing with the shaving mirror and suddenly the world flips upside down, that's not magic. It's a predictable physical boundary. You've just crossed the mirror's focal point. And with the tools we just went over, you now know exactly how to find it.